Thank you everyone for coming here for this network theory reading group. And I'll be happy to present some paper I was reading previously, that is, let's say, surface transition in some discrete and continuum percolation models. And in this talk later, I'll describe one model that I'm looking for some answer, answer like surface transition in that kind of discrete percolation model. So to begin with, I'll start with a very simple example of Bernoulli bond percolation model on Z2 lattice, and I'll define what do we mean by phase transition in this phase transition of percolation in this type of bond percolation model, and then later go to surface transition, and you derive some algorithm that and some inequality that we call as OSSS inequality, that is some variance inequality we have. And then using these inequality and the algorithm, we prove the surface transition. At the end, I'll describe a discrete graph model that we call as whole graph model. Okay, and try to see how we can use this OSSS method to derive the surface transition there. Okay, to start with, let's say you are on a finite window of the Z2 lattice, and at you open or close each edge independently with some probability P. So let's say this is in a finite window, this is one realization of the bond percolation model on Z2 lattice. Okay, so formally this is my model where the vertices are the vertices of the Z2 lattice, and the edges are the nearest neighbor edge, and at each edge is open or closed independently with probability P and 1 minus P respectively. Okay, so the more we have, the higher the value of P is, we have more edges present in the realization. And what is essential is that some properties of the graph will be more likely to be present in the graph if the value of P is more. Okay, so let's say in some physical system where temperature is a parameter, that means let's say you are looking at a fluid, and if you are increasing the temperature, then the fluid will go from liquid state to gaseous state. If you cool it down, then the fluid will turn to a solid state. Okay, so there is a critical temperature below which it is solid, above which it is liquid, and there is another critical temperature above which it is gaseous. Okay, so we see this kind of phenomena, I mean some monotonic phenomena in some physical system. Okay, so this is one example. Another example is some magnetic property of, let's say, some ferrous media. That is, there is a temperature that we call as Curie temperature, that is a critical temperature, below which it is ferromagnet, above which it is paramagnet. Okay, so in our bond percolation model, let's say we denote the graph as GP, that depends on the parameter P, and we call the component of a specific vertex X to be Cx, where we can reach possibly through multiple hops from X to Y, using some path on the graph. Okay, so to go back to our original picture, that is, let's say you want to reach from this vertex to, let's say, somewhere here, maybe this vertex to somewhere here, then you have a path in this graph. Okay, in this realization of the graph. Okay, so, and C of x is the component of x. That means from X wherever you can reach using the path on the graph. Okay, so the connected component, I mean. And we say that a particular vertex X percolates, that means the component should be infinite in the infinite system. Okay, and if you are looking at a finite system, then and if in the finite system there are n number of vertices, then the size of the component of X should be roughly at the scale of n. Then we say that in the finite system the component containing the particular vertex percolates. Okay, so let's say you are looking at the component of the origin and say that what is the probability that the component containing origin percolates. That means the probability that the component is infinite. So using the monotonicity property of let's say using the parameter p, one can say that the higher value is for higher value of p, in the graph, the graph is more likely to percolate, or let's say the component containing origin is more likely to percolate. So that means there exists a critical value of the parameter such that below which our bond percolation model is don't have infinite component at the origin. That means the probability of having an infinite component is 0, but in the supercritical regime, that is, if p is greater than the critical value of the parameter, then the probability of having an infinite component at the origin is positive. Okay, and in a more general case, if we forget about component at the origin, we can say that the graph has infinite component. That probability is of satisfies the Kolmogorov-Zerov law. That means the probability of having a infinite component in the subcritical regime is 0, and in the supercritical regime it is 1. Okay, so in 2 dimension, the critical value of the parameter that was first shown to be half by Kesten in 1980. But what is still not known is what happens in dimension greater than strictly greater than 2. I mean, there are some partial results, but we don't go into that. And let me dive into the main object of this, or the main topic of this talk, that is sharpness of phase transition. So what do we mean by sharpness of phase transition can be seen through this theorem by Duminil-Copin, Raufe, and Tashian, that below the critical value of the parameter, the graph behaves differently than in the supercritical regime. That means if you are looking at a finite box of size n, then there exists a path from the origin to the boundary of the box. That probability decays in n for in the subcritical regime, and in the supercritical regime, the probability of having an infinite path from the origin has a uniform lower bound that has a specific form that depends on a constant as well. So if your random graph, and this can happen to many different type of discrete and continuum random graphs. So but for now we only stick to, let's say, the Bernoulli bond percolation model. So if this type of phenomena is there near critical value of the parameter, then we say that the percolation is or the phase transition is sharp. Okay, because it has exponential decay, and having an infinite component has a uniform lower bound. The probability of having an infinite component, I mean. Okay, so one can see that we are only dealing with some um, some events where you have a path from origin to a boundary of a box or origin to infinity. So we can only deal with some indicator functions and try to indicator function of these type of events and try to find the average value of the indicator function. Let us start with a simple model where that is similar to the Bernoulli bond percolation model, that on the space 0, 1 to the n, you define a function, and this type of indicator function is of, let's say, having a path from the origin to the boundary, can be modeled using this kind of let's say function, where n is, in our model, is the number of edges in a finite window, right? Okay. So on this space 0, 1 to the n, you can write take a argument that is omega, um, and there is a specific, you can define a specific order on this set, partial order, let's say, and then define the specific vector on this space. Okay. So each component of this space of this vector is either 0 or 1 with probability p and 1 minus p, uh, or the other way around. That is, wi is 1 with probability p and wi is 0 with probability 1 minus p. Then you can calculate the average value of this type of Boolean function, that is f from the space to 0, 1. That means f takes value in either 0 or 1. Okay. We say that this um or you can define a sequence of function like that, and then say that this sequence of function undergoes some sharp phase transition if there exists a critical value Pn for each Boolean function Fn, such that just below the critical value, this sequence of function converges to 0, and just above the critical value, the sequence of function converges to 1. So if some Boolean function have this property, then we say that it performs a sharp phase transition. Okay. And one can see some sharp phase transition result using this Margulis-Rousseau's formula. Okay. So let me just state the statement of the result by Margulis and Rousseau separately. That is, if we can write the average value of the function f as f of p, I mean, yeah, the exact expression is here, where this f and this f is different. I mean, I should have used some different notation, but this f is the Boolean function, and this script f is the script f p is a function of p, that is the average value of the function f. Okay. So the script f, it has a derivative that can be determined using some influence. What is the sum of the influence of each coordinate of the vector omega? Okay. So what is the influence? That is, you define for each omega, you define another vector that is, let's say, omega prime, and omega prime is nothing but it is flipped at the ith coordinate. Okay. So then you can define another function that is nabla of f, that is the difference of the function values at these two vectors. Okay. And then try to calculate the expected value of the absolute value of these two differences. That means if you change the ith coordinate of the vector, then how much on average this function is changing. That is the influence, particular influence of a of a coordinate of the vector, right? So the derivative of the average value of the Boolean function can be expressed as sum of the influences of each coordinate on the function. Okay. So keeping in mind, let us try to see how this Margulis-Rousseau's formula can give us half-phase transition of the Boolean function. That is, since the Boolean function takes value only 0 and 1, then the variance, you can calculate the variance of the Boolean function. That is nothing but let's say, the variance of a Bernoulli random variable, right? That is the expected value of f into 1 minus expected value of f. That is f script f times 1 minus script f. Okay. And if we can prove some inequality like this, where the sum of influences is larger than the variance of the Boolean function up to a constant, suppose we can prove that prove such an inequality, then we can use this to prove the surface transition. Okay. So and we also assume that there exists a critical value of the parameter p star such that the script f at p star at the critical value is half, like in our Bernoulli bond percolation model. Okay. And then we can derive a differential inequality using some function of this form, log of fp divided by 1 minus fp. That has, one can calculate this. Then using the variance inequality, and let's say if we go back to Margulis-Rousseau's formula, the sum of influences is nothing but the derivative of the function, right? Not the function, the average value of the function. Okay. And along with the variance inequality, we can say that this ratio is larger than some constant. Okay. Then we have a differential inequality, that is differentiation of this function with respect to p is larger than some constant. Okay. So if the in our bond percolation model, p star is the critical value of the parameter, then we can integrate this differential inequality from p star minus delta to p star. This will give me that if the average value of the Boolean function at p star minus delta, right below the critical value, is exponentially decaying. Okay. And on the other hand, if we integrate this differential inequality from p star to p star plus delta, that means just above a region above the critical value p star, then we get a uniform lower bound like this. Okay. Or it is converging to 1 as delta tends to, let's say, 0. Okay. So we have half-phase transition of this kind of Boolean function.
Sanjoy?
Yeah.
It went a bit fast, sorry. Could you, so you have this differential equation and you integrate them, right? Or but how is it entangled with the assumption that the sum of the influences exceeds C variance of f? How do you, this is needed for the conclusions?
Yeah, it is because you just plug in the this equation for the variance, right? Variance is nothing but script f times 1 minus script f, right? then you plug in the variance on this side,
I see.
and
You
you
need
get this inequality.
you need this in order to write the equations. Okay, different.
Exactly. So this is,
Okay,
yes.
I see.
So
Okay.
the whole talk is about deriving some variance and sum of influence
Okay,
inequality.
so this is the crucial assumption that
This
you
is
will
the
discuss,
crucial.
and under this assumption, by first principles
Yes.
based on these differential equations, you get the result of the sharp phase transition. Okay, thanks.
Exactly.
Sorry.
So I should write this assumption as a display. I mean,
Okay,
it's
okay.
you
Let's
can
say
put it as, sorry.
it's clear. It's clear. I just missed the point. So
Yeah,
thanks.
no problem. You can put this as the title of the talk. So it's
Okay.
no problem. Okay. So our next ingredient of having this kind of variance inequality is to establish some randomized algorithm, and like, I mean, it's bit elaborate here, but let me quickly go through this. That let's say you want to calculate, you want to see what is the value of the Boolean function um, um, given the argument omega. Omega is the vector from the space 0, 1 to the n. Okay, and you want to you don't want to explore all the coordinates of the vector omega. So what you do is algorithmically um, explore the coordinates of the omega before n. If n is the maximum number you can explore. Okay, so let's say at each step um, the coordinate you want to reveal, the coordinate of omega you want to reveal depends on the coordinates you have already revealed. That is given by this equation, and where the psi t is some deterministic rule that you want to impose on all the coordinates that is explored or revealed, and the value at those coordinates for omega. Okay, and you stop when your function no longer changes. It can be 0, it can be 1. Okay, I mean the Boolean function. So this is the stopping time. So it will be more clear when we go back to our original model, that is the bond percolation model. Okay, and if we have an algorithm like this, then we can derive some variance inequality, where along with the influences of each coordinate of the let's say of the vector of omega, there is a probability term involved, that is, that particular coordinate is revealed with what probability, that we called as the revealment probability. Okay, so this is nothing but the probability that the particular coordinate I is revealed before you end the algorithm. Okay, so you get this kind of variance inequality, and using the algorithm. Okay, and this was proved by O'Donnell, Ram, Sachs, and Servadio, and we call it as OSSS inequality. Okay, and this is like the objective was of their work was to show derive some bounds on the complexity of some algorithm. There they derive this kind of variance inequality. Okay.
Sanjoy,
Yes.
you alluded to the special case of the bond percolation. Could you explain what these revealing probabilities are in that case, or you will do that later, perhaps?
I will do that later anyway,
Okay.
but for now I can say that
Hmm.
you want to let's say your Boolean function is having a path from origin to the boundary, right? So you want to explore the path starting from origin and going to the boundary. And if the path does not exist, then the path will stop before you hit the boundary, right?
Yeah.
So at each step of the algorithm, you explore a new edge to enlarge your path to the boundary, right? So it may happen that some of the edges are not explored, so the revealment probability is 0 there, but some of the edges will be explored, right? So, so in your algorithm of finding a path from origin to the boundary, you do not reveal all the edges, but some of the edges are revealed. So it happens randomly that a particular edge is revealed with certain probability.
Okay, I see. I see.
So
Yeah,
that's
so
why
the function that you take depends on the geometry. So you look at the
exactly.
path, and so if you are close to the boundary, it will be easier to reach the boundary.
Yes, yes,
Okay. So
yes,
it's
but
for non-symmetric Boolean function,
yes,
and then you explore things and try to answer the question and look at the sensitivity with respect to the explored things. Okay.
explore things. But there is a simpler way to handle this situation where you reveal the edges far away from the boundary with low probability and close to the boundary, close to the origin with large probability. What you can do is define a sequence of algorithm and average out the revealment probability for each of these algorithm. Okay,
Okay.
take the average of all the algorithms. Okay, so I'll come to that later.
Okay.
Okay,
Thanks.
yeah,
Sorry, just a quick question.
yeah.
What is the definition of tau here in this?
Tau here is okay. It's the time when your function no longer changes in this algorithm. So I mean, you reveal, or let's say only until t, and at t minus one, and let's say your function value on with the vector only until t is one. Okay, then after that it starts it never becomes one again. That means tau is t. Okay, so it will be clear when I define the my actual algorithm for the bond percolation model.
Okay,
I'm
thank you.
sorry, this this may take a few more slides. Sorry. Thanks for the question. Okay, so what is the algorithm in our case? Okay, so to briefly, let's say, recollect what is our vector here. The vector is a point in the space 0, 1 to the e. E is the set of edges in our model. Okay, and you can say it in the finite setting. That is, you take a box of size n, and En is the set of edges in this box. Okay, and each edge is closed or open or closed with probability p and 1 minus p, and the Boolean function we want to explore is the having a path from the having a path from origin to the boundary. And this is the probability that theta n p is the probability that having a path from origin to the boundary. And Sn is sum of all these probabilities until n minus 1. Okay, so we will need this at the end when we prove the subphase transition. Okay, so for now we can let us assume that we have a randomized algorithm, and based on the algorithm we can derive some variance inequality like this. Okay, uh, so later we will see how we can prove the subphase transition using this kind of variance inequality that we have.
Sanjoy, sorry
Yes.
to interrupt again. You say, suppose that we have a randomized algorithm. Could you give an instance in that case?
Uh, I mean, example. You mean the example of a randomized algorithm?
Yes, to do, yes, just because I mean, it was abstract to know, and here it would be good for me to understand
Okay.
what the algorithm mean and what it does.
I mean, the algorithm, what it does is gives you the value of the function, and that
The
is
function
either
Sn, the function Sn.
no, not Sn. This function
Theta? F,
Fn,
the Fn. Okay, the
Fn.
chance
That
to
is
have a path from yes. Okay, yeah.
yes, and that also gives you a path from origin to the boundary. Okay.
But what would be a concrete random algorithm to estimate?
Maybe I'm sorry. Maybe you may have to wait for a
Okay,
couple
okay,
of next slides because it will be.
okay. Sorry.
Yeah, I'm not going into the proof of the surface transition now. So before that, I will go to the randomized algorithm
Okay.
that we need.
You
Okay.
will explain later. Okay,
I
very
will
good.
explain later. Yes.
Thanks. Sorry
Okay.
to interrupt.
No, sorry, no problem. Thank you. Uh, Okay, so yeah, I was always going back to this type of variance inequality just to say that how it is important for the sharp phase transition, for proving the sharp phase transition. Okay, so as I was discussing with Francois, that the in this algorithm, let's say you take just one algorithm that finds you the path from origin to the boundary. Then the edges that are close to the origin that are revealed with larger probability, and the edges that are far away from the origin that is close to the boundary are revealed with very low probability. Okay. To tackle this problem, what we do is change our algorithm a little bit. Okay, for now we assume that we have an algorithm T, okay, that explores the path. But instead of having the T, we derive a set of algorithms Tk for each k between 1 and n. And Tk, what it does is explores the path, explores the connected component of some boundary of a smaller box lambda k, and the connected component should be inside the larger box lambda n. Lambda n is fixed for now, let's say. Okay, and for each k you take the boundary of a smaller box delta lambda k, and you try to explore uh, the connected component of this boundary using some algorithm. Okay. Uh, then if we start from k equal to 1, that is okay, I cannot write, sorry. You can imagine the small box of size 1 around the origin, and what it does is just it gives you one edge that is connected to the origin. If you go one step forward using, let's say, the algorithm T2, what it does is gives you a two-hop path from this box lambda 2 to boundary of this lambda 2 to the origin. Okay, you are exploring the connected component of the boundary, right? So if there is a path from origin to the boundary, then that falls into the connected component of the boundary. Okay. So I have not yet into the actual algorithm that we want to elaborately say, but for now, this sequence of algorithms gives you the revealment probability for each of the edges, right? And you can take the average of all the revealment probability. That gives you that takes care of the bias that you have in your original algorithm. Okay, so this is the way you can say that um, each of the edges are revealed with more or less equal probability. Okay, So let me go to the algorithm that that we were waiting for. Let's say you take take a larger box lambda n and a smaller box lambda k and define an algorithm. So for now, let us say that En is the set of edges in lambda n, and you want to explore the connected component of delta lambda k that is inside lambda n. Okay. Okay. So let me show you this picture. Then I can go back to my original algorithm. That is, you have a larger box lambda n, and you have a smaller box lambda k, and you want to explore the connected component of this boundary of lambda k, and if there exists a path from origin to the boundary, this boundary of lambda k, then it falls into the connected component. If there exists no path, then the origin is not part of the connected component. Okay. Okay. So if you start,
Sanjoy, sorry for the. So in that case, so the value of P is such that there is the connected component. There is a single connected component associated with the boundary, right? But there could be many, right?
There could be many. Yes, yes.
And so if there are many, you still can ask the question whether this connected component has a connection to the origin, right? Through one of the, it could not be a single component, but you could still ask the question whether one of them,
yes,
hits zero, right? That's the question, right?
That's the question. That's true.
I see.
And yes, 2-0 exactly. And the sequence of algorithm. Why we are looking at the sequence of algorithm? Because you can start with k equal to 1, and then say that explore the connected component of capital lambda 1. The boundary of capital lambda 1, and then lambda 2, then lambda 3, then you reach up until lambda n, right? So in this process, you explore all the connected component containing all the connected components of each of these boundaries, right? And this will give you the path. I mean, all of this will give you the path from origin to the boundary if it exists. Okay, because the path that goes to the boundary of lambda n will also hit all of these boundaries, right? So it is better to explore the path for each of these boundaries. For k equal to greater than 1 and less than n. Okay, so how do we construct this kind of algorithm to explore the connected component of delta lambda k? So you start with all the vertices that is lying on this boundary, that we call as V0, and in this algorithm you at each step you grow this set of vertices and you grow some set of edges. So at the boundary you don't have any edge. Okay, and let's say you are at step T. Okay, where your set of vertices in the first step of the algorithm is the vertices on the boundary, and the edge set is empty. Okay, and at step T plus 1, you choose an edge from the unexplored region such that the first vertex of this, one of the vertex of this edge is already explored, but the other one is not explored yet. Okay. If such an edge exists, there can be more. So you at the beginning we have said that you can define a partial ordering on the set of edges. and then you can choose the smallest edge of this ordering if there exists more than one edge like that. Okay, then you grow the set of edges including this particular edge to your set F. Okay, and you can grow update your set of vertices by including this unexplored vertex, that is y, that is not yet explored. Okay, and if it is open, then you include, otherwise you don't include that. Okay, and if at this step of the algorithm, if such type of edge does not exist, that means what? Your endpoint, both the endpoints of the vertices, let's say you stumble upon edge where both the vertices is already explored, then you include that edge, but you don't see any new vertex, right? So you don't update your set of vertices, but you update your set of edges. Okay, so this is our actual algorithm where you keep on exploring the connected component that intersects the boundary of the of the smaller box lambda k. Okay, so I mean the algorithm is about keep on exploring the component. I mean, using the set of algorithm, you can explore the connected component from the origin. If you run all the algorithms T1 to Tn together, okay, and for this set of algorithm, there is a stopping time tau such that you find the path from origin to the boundary. Okay, so one can define this stopping time as that sorry.
Sorry, I have a question. So it is the title of this slide. It is written randomized algorithms, but there is nothing random. If I understood well. Because the way you select the edge is deterministic.
Yes, there is something random because you want when you look at an edge and look at its configuration, it is open or closed with probability p and 1 minus p. That's the algorithm. That's why it is random. Okay, so so that means you update your set of vertices with certain probability, and you don't update with the rest of the probability. Okay, so you can define the stopping time to be the last time when you are in the first case. That means you keep on exploring more vertices, and when you don't keep on exploring more vertices, you keep on exploring the component itself, where you don't grow the set of vertices, but you can grow the set of edges that will complete the component that intersects the boundary. Okay, so I mean, if we go to this picture, let me try to zoom in a bit. Oops, sorry. Yeah. Okay, so let's say you start from the boundary, and then you look at, I mean, it's very small. I should have, yeah. So the algorithm somehow gives you the connected component of that intersects the boundary. Okay. Okay, so let us try to see how this algorithm and the variance inequality is giving us our result. Okay.
Sanjoy, before going to that, could you say one more word on the stopping time? So the stopping time is in K, if I get it correctly, right?
Stopping time is
on K. You increase the algorithm start with K is equal to 1. You grow,
yes.
and look at the connected component of this box.
Yes.
Right?
Yes.
And at one stage, you say, that you see a path from that both connects the root and through this boundary to the extreme boundary, and then you stop, right?
Yes.
That's it?
Yeah. Yeah.
Okay. Thanks.
But for different K, one can probably see that the stopping times is different. But if there exists a path from origin to the boundary, then K tau is same for all the algorithms, right?
Yes, you mean to the outer boundary, the lambda n boundary.
Yes,
right?
lambda n, yes.
To delta lambda n. If you explore one of the lambda k boundaries,
yes.
If you find a path from 0 to lambda n, then you're done, right?
Yes, exactly.
So it's a sort of compromise between the inner structure and the outer structure. Okay.
Exactly.
Thank you. Yeah.
Exactly. And you are not forbidden to explore the edges outside lambda k, but you can still stay inside lambda n. Okay. So if you allow that, then you explore the path from origin to the boundary of lambda n.
Okay. Thanks.
Yeah.
Thank you.
So if let's say for algorithm tk, you reveal the edge, particular edge e, that is x comma y, with probability delta e of tk, then using the algorithm, since you are you start exploring from the boundary of lambda k, that means from this point x you have a path to the boundary of lambda k, and from this point y you also have a path from the boundary of lambda k. So the revealment probability is upper bounded by this union bound. That means the sum of these two probabilities, that your algorithm will tell you that if the particular edge E is revealed, then either there exists a path from the boundary to X, or there exists a path from the boundary to Y. Okay, so this revealment probability is bounded above by these two probabilities, that is having a path from X to the boundary of lambda k and Y to the boundary of lambda k. Okay, and then
just do I get it correctly that the notion of being revealed is that you ask the question to edge E in your exploration when you depart from the lambda k boundary, and to check whether there is a path from 0 to lambda n. If you explore in this thing E, then it is revealed, right?
Yes.
That's
exactly.
it?
Exactly.
Get it now.
Yeah. Yeah, there can be some situation that a particular edge is not revealed, but this comes with a probability, right? So, but a particular path is revealed if there exists a path from the boundary to one of the endpoint of the edge. Okay, so that's why we have this upper bound.
Revealing of edge doesn't mean that it's open. Or not?
It is open, because that's what this algorithm says. It's not necessary. It's not necessary.
But I don't know whether it's open or not without deciding to reveal it.
Yes, yes. So there can be some
some edges that I was trying to reveal.
Yes.
I discovered it's closed.
It's closed. Yes, it can happen.
In the inequality.
It's in the inequality. Yes, yes, that's true. Sorry. Okay, so you can sum this type of revealment probability and try to get an upper bound for this sum, right? So this is a bit tricky part, where let's say you take sum over k on both sides of this inequality, and then if you let's say take the first vertex x, then the probability that there exists a path from x to the boundary of lambda k is nothing but if you draw a box of size k minus, let's say, some value that depends on some distance that depends on x and 0, that is, this distance is nothing but the L1 distance from origin to the point x. So you can draw a box around x and ask the same question that there exists a path from the center of the box, that is x, to the boundary of the box. Okay, and this it is more likely to have a path from this center x to the boundary of the box that is centered at x. Okay, so you can do the same for the other point. So this should be y. This is a typo, I'm sorry. And you can connect it to the function that I have defined earlier, that is Sn. Sn is nothing but the sum of the probability that you have a path from the center, that is origin, to the boundary of box lambda k. Okay, so you can keep on having this type of inequality to get a upper bound for the sum of the revealment probability. Okay, and okay, so if we have algorithm tk, then we have, using the OSSS inequality, we have that a variance inequality that deals with the sum of revealment, deals with the revealment probability and influence of each of the edges. So I should have written this sum as sum over all the edges, not that sum from I equal to 1 to infinity, 1 to n. Okay, this should be sum over all the edges. Okay, for now, let us assume that the number of edges is n, and I is the first edge. Okay, then you derive this OSSS inequality for each of the algorithm, but on the left side this remains the same function, right? Then you can take the sum over k and then try to see how this sum of all the revealment probability behaves. Okay, so in this previous slide we have this inequality on sum of the revealment probability that is upper bounded by all of 4 times all these sums. Okay, so you can use that to derive some inequality like this, where you forget about this part theta prime p. I'll go back to that, but the sum of influences is given by n times the variance of fn divided by this extra constant we have, but the constant depends on n. Okay, so for now what we have, this a lower bound for the sum of influences. So from here one can try to see how, let's say, if we go back to Margulis-Rousseau's formula, there also we had, when we try to use the Margulis-Rousseau's formula to prove the surface transition, we needed this kind of variance inequality, that is, sum of influences is larger than some constant times the variance. Okay, so we have to come up with some idea how to deal with this constant and the variance. Okay, but if we go back to the Margulis-Rousseau's formula, the left-hand side, that is the sum of the influences, is nothing but the differentiation of the probability of having a path from origin to the boundary of lambda n. Okay, so the derivative, you can have a differential inequality now. Okay, and later we can use some result from analysis to show the sharp phase transition. So let me state the result. That is, if you have a function, a real valued function from a compact interval to a compact interval, and the let's say sequence of function, and let's say the function satisfies some inequality like this, where the derivative is lower bounded by some constant that depends on n times the function itself. Okay, and where Sn is the sum of all the functions from 0 to n minus 1. Okay, then we have a result that more or less looks like the sharp phase transition, that is below a critical value you have exponential decay, and above the critical value you have a uniform lower bound. Okay, so using this result from analysis, we can see that the theta np also satisfies the sharp phase transition. Okay, we can just plug in the result to say how this function theta np behaves in the subcritical regime and how it behaves in the supercritical regime, given that you take the limit n tends to infinity on the left side. Okay. Okay. Yeah. So this was our result. I mean, maybe I should go back to the original result, that theta np is exponentially decaying in the subcritical regime, but having infinite path from origin to infinity has a uniform low bound. Okay. How much time do I have? Oh, it's 12.
Minus 3 minutes.
Okay. So at the end, let me say a new model that I'd like to understand and prove a sharp phase transition result on this type of model that is derived from this type of bond percolation model. Let's say you take a realization of the bond percolation model on Z2 lattice, okay, and remove and you take the entire Euclidean space. Okay, let's say for now, let's say it is R2, and remove all the edges, all the edges that you get in this realization. This will divide entire Euclidean domain, Euclidean space in connected peak components, right? So you say that two connected components, these may not be these connected components may not be convex sets. They are like union of cubes. Okay, so you say that, and we say this union of cubes as a whole in the space. Okay, so you say that two holes D1 and D2, they are neighbor if there exists a common bond between them. I mean, I should have said it in for dimension D. In dimension D, bonds are like the bonds are just two-dimensional, the edges, but the faces are the D minus one dimensional cubes. Okay, so so one can construct a graph out of these components that we get when you remove all the bonds from the all the bonds from the realization of a bond percolation model. Okay, and you say that two components are neighbor of each other if there exists a bond between the two components. Okay, and then you can construct this graph G for each of this realization, and then try to see whether this type of graph percolates or not. So you can have some monotonicity property depending on P, that if you increase the P, there will be more and more smaller components. That means the graph in this model will percolate. Okay. So this model was first stated by Hiraoka and Mikami, and what result they have proved that there exists a critical value for this model, and the critical value is non-trivial, and it is given by, let's say you are in dimension D, then this critical value PC is given by lower bounded by PC critical value for the phase percolation model, and upper bounded by 1 minus critical value for the bond percolation model on ZD lattice. Okay, so this result gives us the non-trivial phase transition for this whole graph model. But now I'd like to ask the question whether this type of whole graph model undergoes half phase transition or not. So right below critical value of the parameter PCH, whether you have exponential decay of the probability of having a path from origin to the boundary, or in the supercritical phase, having a probability of having an infinite path has a lower bound, uniform lower bound or not. Yeah, so maybe I don't have time to go to, let's say, the continuum percolation. Maybe we can discuss about it. I'm sorry. These are the references I have. Thank you.
Thank you.